All right, so let me share my screen here. Okay, so this next chapter is called Sequences and Series. This is actually chapter 12, which may surprise you because we just did chapters 1, 2, 3, and 4. So now we're jumping to 12. Why are we doing that? Well, I realized that chapters 1 through 4, you may have realized, are all kind of review of stuff that you learned in Algebra 2 Trig, right? Kind of taking it to the next level, and I hope that you guys understood some stuff a lot better this year. I think based on your test and quiz scores, a lot of you understood logarithms a lot better this year than you did last year, and so that's awesome. But there's some other stuff in math that you guys have never seen before that's actually very important, okay? And so this right here, sequences and series, you have never, if you've gone to Tustin High through your whole career, you haven't seen these before, okay? And so I wanted to make sure you guys were familiar with these because I think they are very important. And I think they're really interesting as well, okay? And they're kind of fun as math can get, right? So let's go through it, okay? So what is a sequence? Well, a sequence is a function expressed as a list of terms, okay? So it's a list of numbers. Let me make a sequence for you right now. 3, 6, 9, 12, 15, 18, 21. That was a sequence. Did the sequence have a pattern? Yes, yeah, and most sequences do have patterns, although even if it didn't have a pattern, it would still be a sequence, okay? There's actually a very famous sequence that has no pattern, the digits of pi. If you read those off, 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8, 9, 7, 9, 3, 2, 3, 8, dot, dot, dot. That's actually a sequence with no pattern, but it's still a sequence if you list them out like that. For those of you wondering how I know those digits of pi, I actually don't have pi memorized I have like 6 digits of pi memorized, but I have a poster of all the digits of, or not all of them, but I have a poster of about 30 digits of pi in my room. So it's actually just reading that off there, okay? Okay, so that's what a sequence is, a list of numbers, okay? A series is the expression that results when the terms of a sequence are added together. So we're going to see there's times where it's beneficial to add all these terms together. We call that a series. We also call that a sigma. It's the Greek letter right here that looks like a funky E. That means the same thing as series. It means add all these terms up, okay? All right, cool. So let's talk about sequences more. So like we said, a sequence is kind of like a function, but the key difference between these, the key kind of distinction on these functions is that the domain is a set of consecutive integers, okay? So domain is what we plug in, correct? So when we had regular functions, were we allowed to do like f of 0.5 or f of 3 over 2? Yeah, we were, correct? But on these functions, sequences, we're only allowed to plug in integers, okay? And we are usually starting by plugging in 1. That's the first integer we plug in. And then go up from there, okay? Consecutive integers. Now, it is possible to start with other numbers like 0 or maybe 2. But for the most part, generally speaking, about 90% of the time, you're going to start by plugging in a 1, okay? So the domain would look like this: 1, 2, 3, 4, and n. And n is going to be like our main variable here for domain, okay? Now for normal functions, x is the main domain variable, right? X is usually what you're plugging in. In this case, we call it n. The range, the output, okay, looks like this. It is an a and then a subscript 1. I'm going to be reading that, and most people read this as a sub 1, okay, because it's a subscript of 1. A sub 2 would be the second term in the list. A sub 3 is the third term. A sub 4 is the fourth term. And A sub n is the nth term. Got it? Okay. We'll also be looking at 2 different types of sequences. Infinite sequences, which go on forever. And then the opposite of that, which is that word up there, which I would guess if most of you said it out loud right now, you'd pronounce it wrong. That is finite sequence. Yeah, most people think that's pronounced finite, which makes sense because if it's infinite, then it should be finite, right? But it's not, it's finite. So finite means it ends, right? There's an ending point to that sequence, okay? Awesome. So let's take a look at our first 2 examples here of sequences. And our goal to start off here is going to be very easy here for the first couple problems, okay? Is it going to get a lot harder after that? You bet. but we'll start off nice and easy, okay? So what they want here is the first 5 terms and then the 100th term. So to find the first term is called a sub 1, and a sub 1 equals, and just like functions, if the subscript over there is a 1 for n, that means I plug in a 1 for n on the right side. So a sub 1 is 2 times 1, which is 2. A sub 2 is 2 times 2, which is 4. A sub 3 is 2 times 3, which is 6. A sub 4 is 2 times 4, which is 8. A sub 5 is 2 times 5, which is 10. And a sub 100 is 2 times 100, which is 200. The first 5 terms and then the 100th term, okay? If we're technically going to write this as a sequence, which I would like to do, you would, like I said earlier, write it as a list of numbers. So I'll go ahead and do that. So I'd say 2, 4, 6, 8, 10, 200. So the first term, a sub 1, is 2. The second term, a sub 2, is 4, and so on and so forth. Not too difficult, right? Okay, let's go ahead and try number 2. Shouldn't be difficult either. You can see that they called this one c sub n. So just like, for functions, usually we use f of x, but you could also use g of x or h of x. Like, you can just call it a different letter, right? But the idea is the same. So c sub 1, 1 squared minus 1. So that's 0. C sub 2 would be 3. C sub 3 would be 8. C sub 4 would be 15. C sub 5 would be 24. C sub 100. 100 squared is 10,000. So this would be 9,999. So my list here would be 0, 3, 8, 15, 24, 9999. Beautiful. Great list of numbers we got going there, right? All right, let's go to the next page where I think it's still going to be pretty easy here. Same idea. We get t sub 1 is 1 over 1 plus 1, so that's 1 over 2. T sub 2, 2 over 2 plus 1, so that's 2 over 3. I'm actually going to stop right there because, like, I know what's going on here, right? I don't need to show my work anymore because I can make this list in my head now. You guys see what I'm saying? Like, every time, the top number is whatever number we're on, so that's 1. And then the bottom number, the denominator, is 1 more than that. So then I have 2 over 3. Then it's going to be 3 over 1 more than 3, so 3 over 4, 4 over 5. The top and the bottom just both increase by 1. I know the 100th term, the numerator is going to be 100, and then the denominator is going to be 1 more than that, right? So at the point that you pick up a pattern and you can stop showing work, feel free to stop showing work, okay? I mean, definitely this year, but even in a normal year where everyone is in class, like, my policy on showing work is show work when you have to show work. And if you don't have to show work, don't show work. If you can do it in your head, do it in your head. That's fine, okay? I understand. Okay, let's take on number 4 then. All right, so number 4, same idea. So r sub 1 is going to be negative 1 to the first power over 2 to the first power. So it's going to be negative 1 on top and a 2 on bottom. R sub 2, we get negative 1 on top squared over 2 squared. R sub 3, negative 1 to the third power over 2 to the third power gives me negative 1 over 8. I'll do the fourth one here. I haven't quite picked up the pattern yet, so I just want to make sure I understand it. So negative 1 to the fourth power is positive 1, and then 2 to the fourth power is 16. All right, I'm going to pause there. I think I can build my list now. But I want to look at this question over here. So what does the negative 1 to the power of n do to the sequence on number 4? Okay, so let's have some participation here. You can type it in the chat or unmute yourself and say it. Can anybody tell me what that negative 1 to the power of n did to this sequence? Take a look at our terms in the sequence and tell me what effect that had on it. How did that negative 1 to the power of n affect the sequence? What are those numbers looking like? My outputs. Yes?
Multiplied it by negative 1.
Okay. And what effect did that have?
It made the sequence have go in positive and negative.
Good. Okay. And Kushi says the same thing that Logan's saying here in class, is that if it's odd, it's negative, and if it's an odd term, it's negative. If it's an even term, it's positive. Yes, it makes the sequence alternate positives and negatives. Okay. Great observation there, Kushi, because that's going to help us going forward. So my terms then I would say are negative 1/2, and then positive 1/4, negative 1/8, positive 1 over 16, negative 1 over 32 would be the fifth term. And then the 100th term, I would say, well, since 100 is an even number, and this is a comma right here, I know it's going to be a positive 1 up top. And then for the denominator, I would just put 2 to the 100 power. When you get these huge exponents, and WebAssign's the same way with this, because that number is so big, like your calculator can't even tell it to you. So if you get a huge exponent, just leave it like that, like 2 to the 100th power, okay? So that's that. So now we know if we have, so now we're going to kind of go the other way with this. You can see that on number 5 through 9 here. Now it's kind of the opposite, okay? So the question looks like our answers, and the answer is going to be like the questions, okay? So we're trying to write a formula for these. But we have a tool now that we can use. If we have those alternating positives and negatives, could we use that negative 1 to the power of n trick that they used? Yes, we could, right? Okay. I'll give you a warning right now. Numbers 5 through 9 here, okay? These are the toughest questions that are in this whole section, all right? Students really struggle with these. So if you're watching us today, and I'm going to really walk us through it and help us on these. But if you're watching this today and like, oh man, this is so difficult, don't feel bad. You're not alone, okay? I will tell you that as we go through the next few sections in this unit, we learn a lot of tricks and formulas that help us out with these. But for now, it's going to be tricky, okay? So just follow along with me. All right, so number 5 here. All right, so number 5, we're trying to write a formula for these fractions here. Now, whenever the formula is all fractions, I would always just draw a big fraction, and I would try to come up with a formula for the top and the bottom separately, okay? So just separate them in your mind. I'm actually going to start with the denominator on this one because I think that's a little bit easier. So let's take a look at the denominator only. How are we going to write a formula for that denominator? Well, what are the numbers in the denominator? 2, 4, 6, 8, okay? Multiply by 2 is correct, multiply by 2 is correct. But let me tell you what most people put on this, okay? Whenever I kind of ask students this one, most students will write this on the denominator. They'll write n plus 2, okay? Now, that's not correct. I'll tell you right now, okay? But the person who writes this, are they stupid? I'm going to say no, okay? They're not right, but they're not stupid either. Like they're saying, "Hey, Mr. Berry, that denominator, the numbers are increasing by 2 every time, right? So n plus 2, that makes sense." But the great thing about these formulas is that we can check them. So let's plug in 1 and see if we get the correct denominator. 1 plus 2, does that give me 2 as my first denominator? No. So I can already tell it's wrong, correct? So good news, we just erase that. That's why they put pencils on erasers, or that's why they put this button on my stylus so I can erase that. Now, Ethan said on the chat, 2n. Let's see if it works, okay? Sometimes you're not sure, but we can check it. So let's plug in 1. 2 times 1. Does that give us our first denominator? Yes. 2 times 2, does that give us our second denominator? Yes. 2 times 3, does that give us our third denominator? Yes. 2 times 4, does that give us our fourth denominator? Yes. Okay, so 2n is correct. Good job, Ethan. All right, what about the numerator? Okay, the way I look at the numerator is always 1 less than the denominator. Look at every single individual numerator, and you notice that it's 1 less than the denominator, correct? Well, if our denominator is 2n, what formula could we use to come up with 1 less than 2n? 1 less than 2n. Sounds good to me. Let's check it though, just to be sure, because these ones I think are so easy to check. So 2 times 1 minus 1, does that give us our first numerator? Gosh darn right it does. 2 times 2 minus 1, does that give us our second denominator? Yes. 2 times 3 minus 1, does that give us our third denominator? Yes. 2 times 4 minus 1 gives us our fourth denominator? Yes. Nailed it. Okay. So there is some trial and error here, right? So if you get it wrong, just check it and adjust it, right? Like that's what this, I would say, is all about. Okay, number 6. First thing I notice on number 6 is we have those alternating positives and negatives again, right? So I'm going to go ahead and use that -1 to the power of n trick that I learned on number 4 for this. That's going to give me the alternating positives and negatives. This one's not a fraction, so I'm not going to draw a fraction line. So now I'm just going to look at the numbers. So forget about the negatives now, since I already took care of that with my -1 to the n power. What are those numbers? 2, 4, 8, 16, 32. Those numbers are significant to me. What are they? Well, I would say that those are the powers of 2. The powers of 2. 2 to the first power, 2 to the second power, 2 to the third power is 8, right? 2 to the fourth power is 16. And so I see this as times 2 to the power of n. So if I plug in, let's say I plug in 3, -1 to the third power is -1, times 2 to the third power is 8, so that gives me my third term of 8. The fourth power, -1 to the fourth power is +1, times 2 to the fourth power is 16. So this does work. Now some of you may be thinking, hey, Mr. Berry, if I put -2 in parentheses and raise that to the power of n, wouldn't that also take care of the alternating positives and negatives while still giving me all those numbers in that list? And to you, I would say, yes, it does. Guess which one of these answers WebAssign says is correct? Both of them. Okay, that's something I love so much about WebAssign, why I think it's such an awesome kind of platform, is that I would guess that their answer key says the bottom one, but even if your answer is different than their answer key, but it's still correct, it marks it as correct. So I think that that's awesome. Now, what I'm going to note over here is that you cannot do this. If you did -2 to the n with no parentheses, that's actually incorrect. That sequence would actually be all negatives. Because of order of operations, you would do the 2 to the n power first, which would be all positives, and then switch them negative. So it would be all negatives. So that's no good. Got to use those parentheses in this case, okay? All right, let's continue on. Once again, we got 3 more here that are difficult. I told you off the bat that these were like the most difficult ones that we're going to do. Okay. Oh, you know what? There's one at the end of this section that's more difficult, but it's similar. Okay. So number 7. I'm looking at number 7, and something's popping out at me. Something I don't like here. Okay. One of these terms is not like the others. Do you guys notice that? Which term is not like the others? The 3, right? That's sticking out like a sore thumb. Like, what is that 3 doing there? Well, is there a way that we could rewrite 3 that would make it look more like all the other ones? I think there is. Not 3 squared. You're on the right track there, Brenda. I'm going to write it as rad 9. Did I really change it? No. Is rad 9 the same thing as 3? Yes. So why do I want that written as rad 9? Well, it's like apples to apples comparison now, right? Like we're looking at everything inside of a radical. So now I think, and actually if I look inside of those radicals now, it makes a pretty good pattern, right? It's that +2 pattern, you know what I'm saying? So I'm going to write my formula now, a sub n equals, I'll draw a big radical. As we saw on number 5, when you have that increasing by 2 pattern, it's going to be something with 2n, okay? Which is also the name of our principal, right? 2n? Dr. 2n? Ha ha ha. Now, it's not just going to be 2n here on number 7, but it's going to have something to do with 2n. So my point is, whenever you see that +2 pattern, think about 2n. If you see like a +3 pattern, think about 3n. You know what I'm saying? So if I just leave it as 2n, if I plug in 1 right now, I'm not going to get 7, right? I'm going to get 2. So what would I need to add to this so that when I plug in 1, I get 7? Well, when you ask it like that, it's got to be 5, right? Don't take my word for it, though. Test it. 2 times 1 plus 5 gives you 7 inside of a radical, doesn't it? 2 times 2 plus 5 gives you 9 inside of a radical, doesn't it? 2 times 3 plus 5 gives you 11 inside of a radical, doesn't it? And 2 times 4 plus 5 gives you 13 inside of a radical, doesn't it? Yes, it does. All right, onward. Number 8. We got another fraction for number 8. So I'm going to draw a big fraction line. I'm going to tackle the numerator and denominator separately. Numerator first. I think the numerator is simpler on this one. I think the numerator is actually very simple. It is changing, right? So if there's ever one where like the number is staying the same the whole time, like just put that number. But if it is changing, we do need a variable. I would say the numerator is just n, right? Like whatever number we're on, that's our number. So for the first term, it's 1. For the second term, it's 2. For the third term, it's 3. For the fourth term, it's 4. Denominator is a little more tricky here, but I do notice something about those 4 numbers in the denominator. Are those 4 numbers in the denominator special numbers? I think so. They're special to me. Well, all numbers are special to me, but these numbers are especially special. These are perfect squares, correct? Perfect squares for sure, okay? But it's kind of the wrong perfect square. Like the first one isn't 1 squared. The first one's 2 squared. The second one is 3 squared. The third one is 4 squared. You know what I'm saying? So I need to add 1 before I square it, okay? Because if I square it right away, I'm going to get the wrong number. So I need to add 1 before I square it. I've seen 3 people in the chat now get the correct denominator here, which is n plus 1 in parentheses, which is saying add 1 before you square it. Very good. Shout out to you. Rachel and Tammy and Adam. All right. Good stuff. All right, number 9, very tricky as well. Okay, like I said, If this is seeming difficult, it is, okay? But remember also, it will get easier. Okay, so number 9, what do I notice? So the first term is rad 5, the second term is 5, and then it gets 5 rad 5 and then 25. The thing I noticed right off the bat is that rad 5 squared is 5, right? Rad 5 squared equals 5. So my initial instinct here would be if I take rad 5 and raise it to the power of n, I know that that's going to work for the first 2 terms at least. Because I know rad 5 to the first power is rad 5, right? Anything to the first power is just itself. I also know that rad 5 squared is 5. So I know it works for those. So now the question is, does that work for 3 and 4, right? Let's check it out. What's a sub 3? Well, according to my formula, that would be rad 5 to the third power. I see that as rad 5 times rad 5 times rad 5, right? Well, if I multiply rad 5 times rad 5, that would just be a regular 5. So it'd be 5 rad 5, which checks out, right? That's what I wanted. I'm feeling pretty good about my formula at this point. Let's check out the fourth power, though. Well, if I pair these guys up, it's going to give me 25 all day, every day. If you wanted to get really savage with this formula, you could write it like this. Five to the power of n over 2. If you're into fractional exponents, which I certainly am. All right, that's a little bonus for you. You can check that out later on your own time, but I'd say the blue one is sufficient for that, okay? Okay, let's keep it going here. Now we're actually going to learn about a new way to write a sequence now, and that's called a recursive sequence, okay? Recursive sequence. So I said that those last 5 questions we did were the hardest ones. So these ones are easier, okay? It's a little complicated to understand these, but once you understand them, these are actually easier, okay? How do I know that these are recursive? Whenever you see like the sub n minus 1 here, that's my indicator that this is recursive. These ones, each term in the sequence is based on the previous term, okay? Now, what's kind of unique about these ones is that you'll notice they actually gave you the first term, right? So on all our previous ones, when we were trying to find the first 4 terms, we had to find the first term on our own. In this case, they told me the first term. They said, hey, find the first 4 terms, but guess what? Here's the first term. It's -2. Well, if they already told me the first term, I would say the next one I should try to find is the second term, right? I don't need to find the first term because they already told me. So I'm saying n is 2, right? So if n is 2, then n minus 1 would actually be 1. So they're saying a sub 2 here equals a sub 1 plus 4. Well, we actually know what a sub 1 is. A sub 1 is -2, correct? So our second term is 2. I could do that again, and this is like the complicated way to do it, but can I tell you guys just the easier way to understand these sequences? Okay, I'll take that as a yes. Whenever you see this a sub n minus 1, I want you guys to just read that as the previous term in the sequence. So for all of these recursive formulas, they're going to tell you, take the previous term and do something to it. What are we doing in this case? Adding 4. That's it. So I'm going to stop showing my work. I'm going to start showing my sequence. Where does my sequence start? It starts at -2. How do I know it starts at -2? It was given, correct? They told me. A lot of people, they always start this with the second term. because that's the first term that they found, and people are like narcissistic, and they're like, oh, that's the first term I found, so that must be the first term. No, 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 don't be a narcissist. It's not the first term you found. It's the first term. First term, a sub 1. For these, it's given, -2. Now to find the next term, this says take the previous term and add 4. So I take -2, add 4. Take 2, add 4. Previous term plus 4. Previous term plus 4. You see how these are actually easier? It tells you what to do. Plus 4, plus 4, plus 4, plus 4. The next one would be 14, and then 18, 22, 26, 30, etc. That's it. Why do they have to tell you the first term? Well, if you told me to do a plus 4 pattern, and you instead told me to start at 50, it would be a totally different sequence, correct? So each term is based on the previous term, so you have to tell me where to start. All right, so same idea on number 10. We're starting off at 2. How do I know we're starting off at 2? They literally told me. First term's a given. Then, to find each subsequent term, I just keep subtracting 5. So, -5. -5. -5. All right. Not too bad, right? Let's keep going. All right, so now our sequence gets a little bit more complicated here on number 11. I'm actually going to show my work on this one because it is a little bit more complicated. So we already know what a sub 1 is 3. So a sub 2 would be 1 plus the previous term divided by 2. So whenever you see that a sub n minus 1, that just means plug in the previous term, whatever it is. It will be changing along the way. So now I got a sub 2 is 2. A sub 3 then is 1 plus the previous term over 2. However, now the previous term is 2. So where am I getting these numbers once again? A sub 1 goes right there, and then this answer goes right there. That position in the top right of this particular fraction is where I'm plugging in the previous term. So that's where this 3 over 2 is going to go in my next round here. So for a sub 4, 1 plus 3 over 2, plugging in my previous term there, over 2. I'm going to add those fractions. Of course, we need common denominator there, so I'm going to turn that into 2 over 2. So we get 5 over 2 over 2 over 1. Multiply by the reciprocal. We get 5 over 4. So my list of my first 4 terms would be 3, 2, 3 over 2, 5 over 4. All right, we got time for one more problem, and it's one of my favorites, number 12. Number 12, you can see what they did that's a little bit different here is they told me the first 2 terms, right? Well, what does this mean over here? A sub n equals a sub n minus 2 plus a sub n minus 1. Well, to me that means if I want a sub 3, I would have to add a sub 1 and a sub 2. So this to me suggests, and this is why they gave me 2 terms to start, each term is the sum of the previous 2 terms. So 1 plus 1 then gives me 2. My 4th term is 1 plus 2. The previous 2 terms is going to give me 3. I'm going to keep going with this. I know I've been doing 4, but I want to keep going. So 2 plus 3 gives me 5. 3 plus 5 gives me 8. 5 plus 8 gives me 13. 21, 34, 55, etc. This is actually a famous sequence. This sequence actually appears in nature all the time. I'll show you guys a quick video about this sequence on Tuesday, the next day we meet, since we have Monday off. But yeah, does anybody know the name of this famous sequence? It's named after an Italian mathematician who did a lot of work with it. It is not to be confused with the fettuccine sequence. It's the and go ahead and write this down, Fibonacci sequence. Not something that's really going to show up on a test here or anything, but just an interesting thing for you to know. This famous sequence, it is oft, I do hear it referenced in, like, I don't know, pop culture or whatever, the Fibonacci sequence. So it's a good thing for you to be familiar with. It's this list of numbers, okay? 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on, okay? Like I said, we'll watch a quick video about that on Tuesday, but for today, I don't know if you guys knew this about me, but I like to throw some memes in there, right? So I happen to have a Fibonacci sequence meme, so let's check that out. So you've heard of the Fibonacci sequence, right? How about some Fibonacci sequins? Look at the numbers of the sequins. 1, 1, 2, 3 sequins, 5 sequins, 8 sequins, 13 sequins. Get it? It's funny. Okay, cool. So that'll about wrap it up for our notes for today. So remember, I'm going to post this video of what we did today, because I did a pretty good job this period, on YouTube, and I'll post that on Schoology. And then I'll make another video that'll be the rest of the section, okay? I would like you guys to do the rest of the section over the weekend, and we can get going on our WebAssign on Tuesday when we get back, all right? So we do have a little bit of homework over the weekend, just the rest of the section with the help of my notes video. That'll be posted this afternoon, so you can do it anytime this weekend. I think it'll be 15 minutes or less, I'm pretty sure, to get the rest of it done. I haven't made it yet, so YOLO. All right, I think that's all I got. So stick around a couple of minutes for questions, but if you don't have any, then we will see you on Tuesday.